So what I want to do next is test your understanding of both the search and insertion procedures by asking you about their running time. So of the following four parameters of a search tree that contains n different keys, which one governs the worst case time of a search or of an insertion? So the correct answer is the third one. So the height of a search tree governs the worst case time of a search or of an insertion. Notice that means merely knowing the number of keys n is not enough to deduce what the worst case search time is. You also have to know something about the structure of the tree. So to see that, just let's think about the two examples that we've been running so far, one of which is nice and balanced, and the other of which contains exactly the same 5 keys, is super unbalanced. It's this crazy linked list in effect. So in any search tree, the worst case time to do a search or an insertion is proportional to the largest number of pointers, left or right child pointers, that you might have to follow to get from the root all the way to a null pointer. Of course, in a successful search, you're going to terminate before you encounter a null pointer, but in the worst case, or an insertion, you go all the way to a null pointer. Now, in the tree on the left, you're going to follow at most 3 such pointers. So for example, if you're searching for 2.5, you're going to follow a left pointer, followed by a right pointer, followed by another right pointer, and then that one's going to be null. So you're only going to follow 3 pointers. On the other hand, in the right tree, you might follow as many as 5 pointers before that 5th pointer is null. For example, if you search for the key 0, you're going to traverse 5 left pointers in a row, and then you're finally going to encounter the null at the end. So it is not constant time, certainly. You have to get to the bottom of the tree. It's going to be proportional to the logarithm in the number of keys. If you have a nicely balanced binary search tree like this one on the left, it's going to be proportional to the number of keys n, as in the 4th answer, if you have a really lousy search tree like this one on the right. And in general, the search time or the insertion time is going to be proportional to the height, the largest number of hops you need to take to get from the root to a leaf of the tree. Let's move on to some more operations that search trees support, but that, for example, the dynamic data structures of heaps and hash tables do not. So let's start with the minimum and the maximum. So by contrast, in a heap, remember, you can choose one of the two. You can either find the minimum easily or find the maximum easily, but not both. In a search tree, it's really easy to find either the min or the max. So let's start with the minimum. One way to think of it is that you do a search for negative infinity in the search tree. So you start at the root, and you just keep following left child pointers until you run out, until you hit a null. And whatever the last key that you visit has to be the smallest key of the tree, right? Because think about it. Suppose you start at the root, right? Suppose that the root is not the minimum. Then where's the minimum got to be? It's got to be in the left subtree. So you follow the left child pointer, and then you just repeat the argument. If you haven't already found the minimum, where's it got to be with respect to the current place? It's got to be in the left subtree. And you just iterate until you can't go to the left any further. So for example, in our running search tree, you'll notice that if we just keep following left child pointers, we'll start at the 3, we'll go to the 1, we'll try to go left from the 1, we'll hit a null pointer, and we return 1. And 1 is indeed the minimum key in this tree. Now, given that we've gone over how to compute the minimum, no prizes to guess how we compute the maximum. Of course, if we want to compute the maximum, instead of following left child pointers, we follow right child pointers by symmetric reasoning that's guaranteed to find the largest key in the tree. It's like searching for the key plus infinity. All right, so what about computing the predecessor? So remember, this means you're given a key in the tree, an element of the tree, and you want to find the next smallest element. So for example, the predecessor of the 3 is 2, the predecessor of the 2 in this tree is the 1, the predecessor of the 5 is the 4, the predecessor of the 4 is the 3. So here I'll be a little hand-wavy just in the interests of getting through all of the operations in a reasonable amount of time, but let me just point out that there's one really easy case, and then there's one slightly trickier case. So the easy case is when the node with the key k has a non-empty left subtree. If that's the case, then what you want is simply the biggest element in this node's left subtree. So I'll leave it for you to prove formally that this is indeed the correct way to compute predecessors for keys that do have a non-empty left subtree. Let's just verify it in our example by going through the trees that have a left subtree and checking that this is in fact what we want. Now, if you look at it, there's actually only 2 nodes that have a non-empty left subtree. The 3 has a non-empty left subtree, and indeed the largest key in the left subtree of 3 is the 2, and that is the predecessor of the 3, so that worked out fine. And then the other node with a non-empty left subtree is the 5, and its left subtree is simply the element 4. Of course, the maximum in that tree is also 4, and you'll notice that is indeed the predecessor of 5 in this entire search tree. So the trickier case is what happens if you have a key with no left subtree at all. Okay, so what are you going to do if you're not in the easy case? Well, given at this node with key k, you only have 3 pointers, and by assumption, the left one is null. So that's not going to get you anywhere. Now, the right child pointer, if you think about it, is totally pointless for computing the predecessor. Remember, the predecessor is going to be a key less than the given key k. The right subtree, by definition of a search tree, only has keys that are bigger than k. So it stands to reason to find the predecessor, we got to follow the parent pointer. Maybe, in fact, more than one parent pointer. So to motivate exactly how we're going to follow parent pointers, let's look at a couple of examples in our favorite search tree here on the right. So let's start with the node 2. So we know we got to follow a parent pointer. When we follow 2's parent pointer, we get to 1. And boom, 1 in fact is 2's predecessor in this tree. So that was really easy. To compute 2's predecessor, it seems that all we have to do is follow the parent pointer. So for another example though, let's think about the node 4. Now 4, when we follow its parent pointer, we get to 5. And 5 is not 4's predecessor, it's 4's successor. Right? We want a key that is less than where we started. We followed the parent pointer and it was bigger. But if we follow one more parent pointer, then we get to the 3. So from the 2, we needed to follow 1 parent pointer. From the 4, we needed to follow 2 parent pointers. But the point is, you just need to follow parent pointers until you get to a node with key smaller than your own. And at that point, you can stop, and that's guaranteed to be the predecessor. So hopefully you found this intuitive. I should say I have definitely not formally proved that this works, and that is a good exercise for those of you that want to have a deeper understanding of search trees and this magical search tree property and all of the structure that it grants you. The other thing I should mention is another way to interpret the terminating criterion. So what I've said is you stop your search of parent pointers as soon as you get to a key smaller than yours. If you think about it a little bit, you'll realize you'll get to a key smaller than yours the very first time you take a left turn. So the very first time that you go from a right child to its parent. Look at the example. When we started from 2, we took a left turn, right? We went up a link going leftward. 2 is a right child of 1, and that's when we got to the predecessor in just 1 step. By contrast, when we started from the 4, our first step was to the right. So we got to a node that was bigger than where we started. 4 is 5's left child, so it's got to be smaller than 5. But the first time we took a left turn on the next step, we got to a node that was not only smaller than 5, but actually smaller from 4, smaller from our starting point. So in fact, you're going to see a key smaller than your starting point the very first time you take a left turn, the very first time you go from a node to a parent, and in fact that node is that parent's right child. So this is another statement which I think is intuitive, but which formally is not totally obvious. And again, I encourage you to think carefully about why these 2 descriptions of the terminating criterion are exactly the same. So it doesn't matter if you stop when you first find a key smaller than your starting point. It doesn't matter if you first stop when you follow a parent pointer that goes from a node that's the right child of a node. Either way, you're going to stop at exactly the same time. So I encourage you to think about why those are the exact same stopping condition. A couple of other details. If you start from the unique node that has no predecessor at all, you're never going to trigger this terminating condition. So for example, if you start from the node 1 in the search tree, not only is the left subtree empty, which says you're supposed to start traversing parent pointers, but then when you traverse a parent pointer, you only go to the right. You never turn left. And that's because there's no predecessor. So that's how you detect that you're at the minimum of a search tree. And then, of course, if you wanted to compute the successor of a key instead of the predecessor, obviously you would just flip left and right throughout this entire description. So that's the high-level explanation of all of these different ordering operations, minimum, maximum, predecessor, and successor, work in a search tree. Let me ask you the same question I asked you when we talked about search and insertion. How long do these operations take in the worst case? Well, the answer is the same as it was before. It's proportional to the height of the tree, and the explanation is exactly the same as it was before. So to understand the dependence on the height, let's just focus on the maximum operation as is stated in the question. The other three operations, the running time is proportional to the height in the worst case for exactly the same reasons. So what does the max operation do? Well, you start at the root and you just follow right child pointers until you run out of them, until you hit null. So, that the running time is going to be no worse than the longest such path. It's a particular path from the root to essentially a leaf. So it's never going to have running time more than the height of the tree. On the other hand, for all you know, the path from the root to the maximum key might well be the longest one in the tree. It might be the path that actually determines the height of the search tree. So for example, in our running unbalanced example, that would be a bad tree for the minimum operation. If you look for the minimum in this tree, then you'd have to traverse every single pointer from 5 all the way down to 1. Of course, there's an analogous bad search tree for the maximum operation, where the 1 is the root and the 5 is all the way down as a leaf. Another thing you can do with search trees, which mimics what you can do with sorted arrays, is you can print out all of the keys in sorted order in linear time, with constant time per element. Obviously, in a sorted array, this is trivial. You just use a for loop starting at the beginning, going to the end of the array, printing out the keys one at a time. And there's a very elegant recursive implementation for doing the exact same thing in a search tree. And this is known as an in-order traversal of a binary search tree. So as always, you begin at the beginning, namely at the root of the search tree. And a little bit of notation, let's call all of the search tree that starts at r's left child t sub l, and the search tree rooted at r's right child t sub r. In our running example, of course, the root is 3. T sub l would correspond to the search tree comprising only the elements 1 and 2. T sub r would correspond to the subtree comprising only the elements 5 and 4. Now remember, we want to print out the keys in increasing order. So in particular, the first key we want to print out is the smallest of them all. So something we definitely don't want to do is we don't want to first print out the key at the root. For example, in our search tree example, the root's key is 3. We don't want to print that out first. We want to print out the 1 first. So where's the minimum lie? Well, by the search tree property, it's got to lie in the left subtree t sub l. So we're just going to recurse on t sub l. So by the magic of recursion, or if you prefer induction, what recursing on t sub l is going to accomplish is we're going to print out all of the keys in t sub l in increasing order, from smallest to largest. Now that's pretty cool, because t sub l contains exactly the keys that are smaller than the key at the root. Remember, that's the search tree property. Everything bigger than the root's key has to be in the left subtree. Everything bigger than the root's key have to be in its right subtree. So in our concrete example, this first recursive call is just going to print out the keys 1 and then 2. And now, if you think about it, it's the perfect time to print out the key at the root, right? We want to print out all the keys in increasing order. We've already done everything less than the root's key. We're, recursing on the right-hand side will take care of everything bigger than it. So in between the two recursive calls, and this is why it's called an in-order traversal, that's when we want to print out r's key. And clearly this works in our concrete example. The reverse recursive call prints out 1 and 2. It's the perfect time to print out 3, and then the recursive call will print out 4 and 5. And more generally, the recursive call on the right subtree will print out all of the keys bigger than the root's key in increasing order, again by the magic of recursion or induction. So the fact that this pseudocode is correct, the fact that this so-called in-order traversal indeed prints out the keys in increasing order, is a fairly straightforward proof by induction. It's very much in the spirit of the proofs by induction of correctness of divide and conquer algorithms that we discussed earlier in the course. So what about the running time of an in-order traversal? The claim is that the running time of this procedure is linear. It's O of n, where n is the number of keys in the search tree. And the reason is there's exactly one recursive call for each node of the tree, and constant work is done in each of those recursive calls. In a little more detail, so what does the in-order traversal do? Well, it prints out the keys in increasing order. In particular, it prints out each key exactly once. Each recursive call prints out exactly one key's value. So there's exactly n recursive calls, and all a recursive call does is print one thing. So n recursive calls, constant time for each, that gives us a running time of O of n overall. In most data structures, deletion is the most difficult operation, and in search trees, they're no exception. So let's get into it and talk about how deletion works. There are 3 different cases. So the first order of business is to locate the node that has the key k, to locate the node that we want to get rid of. All right, so for starters, maybe we're trying to delete the key 2 from our running example search tree. So the first thing we need to do is figure out where it is. So there are 3 possibilities for the number of children that a node in a search tree might have. It might have 0 children, it might have 1 child, it might have 2 children. Corresponding to those 3 cases, the deletion pseudocode will also have 3 cases. So let's start with the happy case, where there's only 0 children, like in this case where we're deleting the key 2 from the search tree. Then, of course, we can, without any reservations, just delete the node directly from the search tree. Nothing can go wrong. There's no children depending on that node. Then there's the medium difficult case. This is where the node containing k has 1 child. An example here would be if we wanted to delete 5 from the search tree. So the medium case is also not too bad. All you got to do is splice out the node that you want to delete. That creates a hole in the tree, but then that node, deleted node's unique child assumes the previous position of the deleted node. I could make a nerdy joke about Shakespeare right here, but I'll refrain. For example, in our 5-node search tree, if we wanted to, let's say we haven't actually deleted 2 out of this one. If we wanted to delete the 5, we take it out of the tree, that would leave a hole, but then we just replace the position previously held by 5 by its unique child 4. And if you think about it, that works just fine in the sense that that preserves the search tree property. Remember, the search tree property says that everything in, say, a right subtree has to be bigger than everything in the node's key. So we've made 4 the new right child of 3, but 4 and any children that it might have were always part of 3's right subtree. So all that stuff has got to be bigger than 3. So there's no problem putting 4 and possibly all of its descendants as the right child of 3. The search tree property is in fact retained. So the final difficult case then is when the node being deleted has both of its children, has 2 children. So in our running example with 5 nodes, this would only transpire if we wanted to delete the root, if we wanted to delete the key 3 from the tree. The problem, of course, is that you can try ripping out this node from the tree, but then there's this hole, and it's not clear that it's going to work to promote either child into that spot. You might stare at our example search tree and try to understand what would happen if you tried to bring 1 up to be the root, or if you tried to bring 5 up to be the root. Problems would happen. That's what would happen. This is an interesting contrast to when we face the same issue with heaps, because the heap property is in some senses perhaps less stringent. There we didn't have an issue. When we wanted to delete something with 2 children, we just promoted the smaller of the 2 children, assuming we wanted to export and extract min operation. Here we're going to have to work a little harder. In fact, this is going to be a really neat trick. We're going to do something that reduces the case of 2 children to the previously solved cases of 0 or 1 children. So here's the very sneaky way we identify a node to which we can apply either the case 0 or the case 1 operation. What we're going to do is we're going to start from k, and we're going to compute k's predecessor. Remember, this is the next smallest key in the tree. So for example, the predecessor of the key 3 is 2. That's the next smallest key in the tree. In general, let's call k's predecessor L. Now, this might seem complicated, right? We're trying to implement one tree operation, namely deletion, and all of a sudden we're invoking a different tree operation predecessor, which we covered a couple slides ago. And to some extent, you're right, delete, this is a non-trivial operation, but it's not quite as bad as you think, for the following reason. When we compute this predecessor, we're actually in the easy case of the predecessor operation, conceptually. Remember, how do you compute a predecessor? Well, it depends. What does it depend on? It depends on whether you've got a non-empty left subtree or not. If you don't have a non-empty left subtree, that's when you got to do this thing where you follow parent pointers upward until you find a key which is smaller than where you started. But if you've got a left subtree, then it's easy. You just find the maximum of the left subtree, and that's got to be the predecessor. And remember, finding maximum are easy. All you do is follow right child pointers until you can't anymore. Now what's cool is, because we only bother with this predecessor computation in the case where k's node has both children, we only have to do it in the case where it has a non-empty left subtree. So really, when we say compute k's predecessor L, all you got to do is follow k's left child, that's not null because it has both children, and then follow right child pointers until you can't anymore, and that's the predecessor. Now here's the fairly brilliant part of the way you implement deletion in a search tree, which is you swap these 2 keys, k and l. So for example, in our running search tree, instead of this 3 at the root, we would put a 2 there. And instead of this 2 at the leaf, we would put a 3 there. Now, the first time you see this, it should strike you as a little crazy, maybe even cheating, like we're just completely disregarding the rules of search trees. And actually it is. Like, check out what happened to our example search tree. We swapped the 3 and the 2, and this is not a search tree anymore, right? So we have this 3, which is in 2's left subtree, and the 3 is bigger than the 2. And that is not allowed. That is a violation of the search tree property. Oops. So how can we get away with this? We can get away with this because we're going to delete 3 anyways. So we're going to wind up with a search tree at the end of the day. So we may have messed up the search tree property a little bit, but we've swapped k into a position where it's really easy to get rid of. Well, how did we compute k's predecessor L? Ultimately, that was the result of a maximum computation, which involves following right child pointers until you get stuck. And L was the place we got stuck. What does it mean to get stuck? It means L's right child pointer is null. It does not have 2 children. In particular, it does not have a right child. Once we swap K's into L's old position, K now does not have a right child. It may or may not have a left child. In the example on the right, it does not have a left child either in its new position, but in general, it might have a left child. But it definitely doesn't have a right child because that was a position at which a maximum computation got stuck. And if we want to delete a node that has only 0 or 1 child, well, that we know how to do. That we covered on the last slide. Either you just delete it, that's what we do in the running example here, or in the case where k's new node does have a left child, you would do the splice out operation. So you would rip out the node that contains k, and the unique child of that node would assume the previous position of that node. Now, an exercise which I'm not going to do here, but I strongly encourage you to think through in the privacy of your own home, is that, in fact, this deletion operation retains the search tree property. So roughly speaking, when you do this swap, you can violate the search tree property, as we see in this example, but all of the violations involve the node you're about to delete. So once you delete that node, there's no other violations of the search tree property, so bingo, you're left with a search tree. The running time, this time no prizes for guessing what it is, because it's basically just one of these predecessor computations plus some pointer rewiring, just like predecessor and search. It's going to be governed by the height of the tree. So let me just say a little bit about the final 2 operations mentioned earlier, select and rank. So remember, select is just the selection problem. I give you an order statistic like 17, and I want you to return the 17th smallest key in the tree. Rank is I give you a key value, and I want to know how many keys in the tree are less than or equal to that value. So to implement these operations efficiently, we actually need one small new idea, which is to augment binary search trees with additional information at each node. So now a search tree will contain not just a key, but also information about the tree itself. So this idea is often called augmenting your data structure, and perhaps the most canonical augmentation of a search tree like these is to keep track of each node, not just of a key value, but also of the population of tree nodes in the subtree that's rooted there. So let's call this size of x, which is the number of tree nodes in the subtree rooted at x. So to make sure you know what I mean, let me just tell you what the size field should be for each of the 5 nodes in our running search tree example. So again, remember, we're thinking about how many nodes are in the subtree rooted at a given node, or equivalently, following child pointers from that node, how many different tree nodes can you reach? So from the root, of course, you can reach everybody. Everybody's in the tree rooted at the roots. So the size there is 5. By contrast, if you start at the node 1, well, you can get to the 1, or you can follow the right child pointer to get to the 2. So at the 1, the size would be 2. At the node with the key value 5, for the same reason, the size would be 2. At the 2 leaves, the subtree rooted at a leaf is just the leaf itself, so there the size would be 1. There's an easy way to compute the size of a given node once you know the size of its 2 subtrees. So if a given node in a search tree has children y and z, then how many nodes are there in the subtree rooted at x? Well, there's those that are rooted at y. There are those in the left subtree. There are those that are reachable from z. That is, there are the children that are also children of z. And then there's x itself. Now, in general, whenever you augment a data structure, and this is something we'll talk about again when we discuss red-black trees, you got to pay the piper. So the extra data that you maintain, it might be useful for speeding up certain operations, but whenever you have operations that modify the tree, specifically insertion and deletion, you have to take care to keep that extra data valid, to keep it maintained. Now in the case of these subtree sizes, they're quite straightforward to maintain under insertion and deletion without affecting the running time of insertion and deletion very much. But that's something you should really think about offline. For example, when you perform an insertion, remember how that works. You do essentially a search. You follow left and right child pointers down to the bottom of the tree until you hit a null pointer. Then that's where you stick the new node. Now what you have to do is you have to trace back up that path, all of the ancestors of the new node you just inserted, and increment their subtree sizes by 1. So let's wrap up this video by showing you how to implement the selection procedure given an order statistic in a search tree that's been augmented so that at every node you know the size of the subtree rooted at that node. Well, of course, as always, you start at the beginning, which in a search tree is the root. And let's say the root has subchildren y and z. Y or z could be null, that's no problem. We just think of the size of a null node as being 0. Now, what's the search tree property? It says the keys that are less than the keys stored at x are precisely the ones that are in the left subtree at x. The keys in the tree that are bigger than the key at x are precisely the ones you're going to find in the x's right subtree. So suppose we're asked to find the 17th order statistic in a search tree, the 17th smallest key that's stored in the tree. Where is it going to be? Where should we look? Well, it's going to depend on the structure of the tree, and in fact, it's going to depend on the subtree sizes. This is exactly why we're keeping track of them, so we can quickly make decisions about how to navigate through the tree. So for a simple example, suppose that x's left subtree contains, say, 25 keys. So remember, y knows locally exactly what the population of its subtree is. So in constant time from x, we can figure out how many keys are in y subtree, and let's say it's 25. Now, by the defining property of search trees, these are the 25 smallest keys anywhere in the tree, right? X is bigger than all of them. Everything in X's right subtree is bigger than all of them. So the 25 smallest order statistics are all in the subtree rooted at Y. Clearly, that's where we should recurse. Clearly, that's where the answer lies. So we can recurse on the subtree rooted at Y, and then we are again looking for the 17th order statistic in this new smaller search tree. On the other hand, suppose when we start at X and we ask Y, how many nodes are there in your subtree, and maybe Y locally has stored the number 12. So there's only 12 things in X's left subtree. Well, okay, X itself is bigger than all of them, so X is going to be the 13th biggest order statistic. It's going to be the 13th biggest element in the tree. Everything else is in the right subtree. So in particular, the 17th order statistic is going to be in the right subtree. So we're going to recurse in the right subtree. Now, what are we looking for? We're not looking for the 17th order statistic anymore. The 12 smallest things are all in X's subtree. X itself is the 13th smallest, so we're looking for the 4th smallest of what remains. So the recursion is very much along the lines of what we did in the divide and conquer selection algorithms earlier in the course. So to fill in some more details, let's let A denote the subtree size at Y. And if it happens that X has no left child, we'll define A to be 0. So the super lucky case is when there's exactly I-1 nodes in the left subtree. That means the root here, X, is itself the ith order statistic. Remember, it's bigger than everything in its left subtree, it's smaller than everything in its right subtree. But in the general case, we're going to be recursing either on the left subtree or on the right subtree. We recurse on the left subtree when its population is large enough that we're guaranteed it encompasses the ith order statistic. And that happens exactly when its size is at least I. That's because the left subtree has the smallest keys that are anywhere in the search tree. And in the final case, when the left subtree is so small that not only does it not contain the ith order statistic, but also X is too small to be the ith order statistic, then we recurse in the right subtree, knowing that we've thrown away A plus 1, the A plus 1 smallest key values anywhere in the original tree. So correctness of this procedure is pretty much exactly the same as the inductive correctness for the selection algorithms we discussed earlier. In effect, the root of the search tree is acting as a pivot element, with everything in the left subtree being less than the root, everything in the right subtree being greater than the element in the root. So that's why the recursion is correct. As far as the running time, I hope it's evident from the pseudocode that we do constant time each time we recurse. How many times can we recurse? Well, we keep moving down the tree. The maximum number of times we can move down the tree is proportional to the height of the tree. So this, again, is proportional to the height. So that's the select operation. There is an analogous way to write the rank operation. Remember, this is where you're given a key value and you want to count up the number of stored keys that are less than or equal to that target value. Again, you use these augmented search trees, and again, you can get running time proportional to the height, and I encourage you to think through the details of how you'd implement rank offline.